Let's get started. Thanks everyone for coming to the special NPA seminar this afternoon. It's a pleasure to have Weiran from MIT. He joined MIT in 2019 as a graduate student. He got his undergraduate degree from Tsinghua University, and he has been doing work on neutrino mass measurements and also new detector technology for future ideas. And so he'll tell us a little bit about the challenges and prospects of absolute neutrino mass measurement.
Thank you for the warm introduction. So today I will give you some insights into direct neutrino mass measurements and talk a little bit about the challenges and prospects in the next 10 years. So I will start with a brief introduction on the neutrino mass from beta-decay. The history of neutrino mass originates from Wolfgang Pauli, who first proposed the existence of neutrinos because of the observation of a spectral distribution of electron energy from a beta-decay. So if there will be no neutrinos, it will be a two-body decay, and you would only expect a sharp peak at this spectrum. But then from this distribution, Wolfgang Pauli realized there might be some new particle that is sharing the final state momentum in this reaction. So interestingly, he proposed that there was some neutral particle which could have mass at the same order of magnitude as electron mass. So neutrinos were proposed not with a zero mass, but with a tiny mass. It was thought that neutrinos are massless because in very long time, people have not observed any right-handed neutrino or left-handed anti-neutrino, which means neutrinos are traveling with the speed of light, and therefore neutrinos were regarded as massless from the standard model. However, people have realized the issue from the solar and atmospheric neutrino problems, where the solar neutrino flux and atmospheric neutrino flux were observed to be smaller than it would be expected. So there's a disappearance of these two flavors of neutrinos, which indicates neutrino oscillation. Basically, one flavor of neutrino can be oscillated into another flavor. And to explain this, neutrinos must have a non-zero mass or a non-zero mass splitting in between its different eigenstates. And this has been verified by the Super Kamiokande and the SNOW experiment. I have a big picture of the SNOW detector here. They have measured that the neutrino mass splittings in between these mass eigenstates are at most at the order of 10 to minus 3 electron volts squared. But both of these measurements for neutrino oscillation would have no hint on what the absolute mass scale looks like. So the neutrino mass scale can be probed in different scenarios. We have cosmology, we have neutrino stable beta-decay, and also the single beta-decay. In cosmology, the observable here is the sum of neutrino mass. And the most stringent constraint comes from the DESI and CMB combined analysis, which was only available last month. So the upper limit here is 0.064 for the sum of neutrino mass, which is slightly in contradictory with neutrino oscillation results. So people have been claiming that cosmological observations have ruled out or almost ruled out the existence of neutrino mass. But of course, this is model dependent because they use the lambda CDM model as the input. And the second approach would be to probe neutrinoless double beta decay, where the observable looks like this. And currently, the best upper limit is provided by Kamda and Zheng with a range corresponding to different calculations of nuclear matrix elements. Here, the search is only sensitive to Majorana neutrinos. So if neutrinos would have a Dirac mass, they would not be sensitive. So this is also model dependent. And the third and last probability would be to probe it with a single beta decay, where the observable is the sum of square neutrino mass being weighted by their mixing matrix elements. The current best upper limit is 0.45 electron volt from the KATRIN experiment, and that is the main focus of this talk. It does not have any model dependency except for the kinematics of this beta decay. So we would call it a direct and model independent search by precisely measuring the beta decay spectrum around the endpoint region. And let me tell you a little bit more about neutrino mass from tritium beta decay. A tritium atom can have a beta decay into helium-3, electron, and electron anti-neutrino. It has several advantages, including that it's a super allowed transition such that the nuclear transition matrix does not depend on energy. So we have a quite simple form of this spectrum. And also tritium has a short decay time with a half-life of about 12 years, which means we can get a decent amount of statistics in a certain certain range of data taking period. And also it has a low endpoint energy, which maximizes the amount of event in the region of interest. Here I'm showing you the effect from a non-zero neutrino mass and the distortion of the beta decay spectrum around the endpoint region. For atomic tritium beta decay, because it's a super allowed transition, the decay rate is proportional to a Fermi function multiplied by the phase space term of the electron and of course also the neutrino. And here in the neutrino momentum term, mu squared comes up. And that's why this probe is sensitive to neutrino mass. As you can see, we are directly measuring mu squared instead of mu. And because the probe currently is still at a scale larger than the mass splittings, and it does not have the sensitivity to really distinguish between different neutrino mass eigenstates, we are measuring a coherent summation of different neutrino mass eigenstates, as you can see here. So we don't separate these different contributions from different mass eigenstates, we treat it as a whole. Breaking the degeneracy and really looking at the contributions from different mass eigenstates would require an energy resolution of about 0.01 electron volt. Now here comes another story, because atomic tritium does not naturally exist in nature. It instead exists in the form of molecular states. A molecular tritium can decay meanwhile producing some final state energy distribution by the rotation and vibration of this molecule. So for molecular tritium decay spectrum, it needs to be modified and taking into account the probability of falling into a certain final state with a given energy. In this plot, I'm showing the energy distribution of the final state, and basically the total spectrum is a sum over all these possible states. It is worthwhile noticing that a sensitivity of certain neutrino mass is limited in this case because of the intrinsic broadening of this ground state of molecular tritium. Now, with the background information, I'll talk a little bit more about the KARlsruhe TRItium Neutrino experiment, also known as the KATRIN experiment. This is an overview of the KATRIN experiment. The molecular tritium are injected from the tritium source, and they propagate freely into both directions in this so-called windowless gaseous tritium source. And at the rear part, there are calibrations with the electron gun and also the rear wall to end those magnetic fields. On the other side, the decayed electrons will be transported through the transport and pumping system and then enter the main spectrometer. We apply a negative high voltage in between the source and the main spectrometer to select out electrons with sufficiently high energy. And those being selected would pass the so-called analyzing plane and get detected by the detector. And here's the internal view of the main spectrometer, and also this transportation picture tells you the scale of the main spectrometer. Now let's take a closer look of what happens inside the main spectrometer. So electrons start from a quite strong magnetic field, and magnetic field gets decreased to its minimum at the center of the main spectrometer, which we call analyzing plane. In this process, electrons will have their transverse momentum being transformed into its longitudinal direction because of the adiabatic invariant being the magnetic moment. So with a minimum magnetic field in the center, the transverse energy will almost be zero, which makes all its momentum lying like in parallel to the magnetic field line. And we apply a negative high voltage in between this analyzing plane and the source. If the electron energy is higher than the high voltage we apply, it can pass this analyzing plane and get accelerated by the electric field towards the detector and eventually get detected. If an electron does not have enough energy to pass through this electrostatic barrier, it will be reflected back to the source and never be detected. So this is how KATRIN selects out electrons. It selects out those electrons with its transverse energy, with its longitudinal energy being greater than 0 at the analyzing plane. And therefore, KATRIN performs a so-called integrated measurement. As you can see here, if we have a beta decay rate or a differential shape of this, what we measure looks like the red line. Basically, at every point, you integrate from this towards infinity, and you sum over all these electrons, and all these parts can get detected. All the parts on the left-hand side or with lower energy will not be detected. And therefore, the detected rate would be equal to an integration from your high voltage set point to infinity. But this is the ideal case, because at the source, we have electrons being emitted in all different directions, which means they will have a different starting transverse energy. And from this adiabatic transportation, there would still be a remaining part of this transverse energy at the level of 1 electron volt, which will never be selected out by applying an electrostatic field. Therefore, this missing energy represents the energy resolution of the main spectrometer, which is also at the level of about 1 electron volt. As I have introduced to you the integrated spectrum, it looks basically like this. And we also have a background added to it. So as you can see, we have some measurement points above where tritium decay can happen. These points help us to constrain the background rate. And we optimize the measurement time to be close to the endpoint just to maximize the sensitivity on neutrino mass, because neutrino mass will only distort the spectrum close to the endpoint side. So you can see the distortion of the spectrum in the middle panel is a neutrino mass being about 0.3 electron volts. We have several main background sources. The one major contribution comes from a steady state background, which does not depend on the high voltage setup, which is predominantly from river atoms. And to account for different transmission conditions to pass the main spectrometer, there's also a high voltage dependent slope taken into account, which is exaggerated by multiplying by a factor of 10, and it's illustrated in orange here. So actually, it's a quite tiny contribution. The third contribution comes from the so-called pending background, which are originated from the part in between the pre and main spectrometer, and those electrons trapped in between these high voltage set points. But I'll talk about it later. Now I'll give you some information on KATRIN analysis and also its latest results. Here's the timeline. We started data taking in 2019, and for the results reported here, we have the first 5 measurement campaigns included. And now we're at 2025, so we have another large fraction of data set that we have not taken into account yet. And KATRIN is expected to finish data taking by the end of 2025, reaching a total amount of 1,000 days of data taking. It'll be horribly before 1,000. And this is the projection of the last few campaigns that have not happened yet. So in total, 80% of the statistics have already been collected, and of which about 20% are analyzed and reported in this talk. When we reach the end of 2025, KATRIN is expected to have a final sensitivity of 0.3 electron volt at a 90% confidence level. This is the measured spectra from the first 5 measurement campaigns, and one measurement campaign would usually be about 2 months in its time. As you can see, we have an improved signal to background ratio if you compare the later campaigns with the previous campaigns. And also, we have improved on a large fraction of systematic uncertainties. This is a comparison of the second campaign and the 5th campaign. And you can see most of the systematic uncertainties have either been totally suppressed or have been reduced to a lower level. Here, the only exception is that gas density and energy loss actually have a higher contribution in the combined analysis, and I will tell you why. But generally, we already figured out and optimized the setup to really suppress the systematic uncertainties, and which allows for KATRIN to reach its final sensitivity. In the first 5 campaigns, we tried different setups, and we found that the main background source coming from Rydberg atoms is really a bottleneck for us to reach the final sensitivity. So Rydberg atoms exist from the alpha decay of chromium, which are then ionized by blackbody radiation. Those ionized electrons have a starting energy of about milli-electron volt. And if they are created in the left-hand part of this main spectrometer, they will not have enough energy to pass the electrostatic field, and they will not contribute to the background. But if they are generated on the right-hand side, then yes, they will be guided by the electric field and travels toward the detector. So you could see that this kind of background actually depends on the volume in between the analyzing plane and the detector. So there was an idea, okay, maybe we could shift the analyzing plane more towards the detector part, where analyzing plane represents the plane where we have a minimal magnetic field. This was performed in the 3rd campaign. We had 2 short runs to verify its performance. And as you can see, with the analyzing plane in the center, which we call a normal analyzing plane, its background rate is about twice of that with a shifted analyzing plane. More details can be found in this paper. In addition, we have also eliminated the background from the panning trap in between the pre and main spectrometer. Those backgrounds are mainly produced by the positive ions from electron tritium scattering. And because positive ions will be guided from the electrostatic field towards here, be accelerated and decelerated, and they will always be detected by the detector, they would inevitably contribute to our background. These were removed previously with conductive wiper after each scan step. But in the recent campaigns, we have reduced the potential of pre-spectrometer, which means the panning trap in between these 2 spectrometers no longer exists. So we don't observe any kind of panning background starting from 2021. The source and field calibration in that systematic table was performed with krypton-83. Krypton-83 has a well-known energy and a negligible natural line width of its N2-3 line, which makes it an ideal source for us to calibrate the energy scale of the KATRIN spectrometer. We measure the line positions of these well-known N2-3 lines and compare them with literature values. And this calibrates our analyzing plane fields. If we observe any extra line broadening of these lines, that means we have a source potential variation. So by performing this, we really have a very nice calibration of the source and the field part. And the stronger activity that we have in the krypton source, the better precision we can get and to suppress these systematic uncertainties. There was a new krypton co-circulation mode together with tritium gas starting from April 2020. And with that, we increased the source temperature from 30K to 80K. We also have a measurement on the column density, which is the density of the gas inside the source, and also the energy loss. which represent basically the loss of energy from electrons scattering of the tritium atoms inside the source. There are two kinds of measurements in this calibration. The first one is a so-called integral measurement, where we shoot monoenergetic electrons from the electron gun, let it pass the main spectrometer with a high voltage set point. If they have sufficient energy, they will be able to pass and be detected. So this measures something which looks exactly in the form of the response function. And it has an advantage that in the tail region, it has quite high statistics because there we have more electrons being able to pass and detect it. Another mode is the so-called time of flight measurement, where we have an energy-dependent time of flight for electrons traveling from the beginning to the detector. Because by applying different high voltage, those electrons will travel slower if they have a smaller energy at the analyzing plane. So this performs a differential measurement, and it is sensitive to these narrow peaks. In this case, the main spectrometer serves as a narrow bandpass filter, and it has a better resolution in separating these sharp peaks compared with the integral measurement. We have both of these calibration measurements performed, but the thing is that we observed a disagreement in between these two methods. So we decided, okay, for now, we should really increase the systematic budget to include both of them. But we are planning to have a better modeling of the energy loss function to resolve this discrepancy. And this explains why from the previous picture, you saw that column density and energy loss systematics are increasing. And with all of this in mind, we have derived the current world-best neutrino mass limit. On the left-hand side, you can see the profile likelihood for all these separated campaigns, with the first campaign lying actually at the more negative region, but the following campaigns dragging the neutrino mass square more to the positive part. We performed the so-called Log-of-Katrov construction, which is not exactly the same as the well-known Feldman-Cousins construction, but that takes into account that we should not report a neutrino mass upper limit better than our sensitivity. So if we measure a negative best fit of mu squared, we don't report a lower upper limit compared with we measure a 0 mu squared. That is because we believe that we should not be benefiting from a under fluctuation, because that could also be some misunderstanding of the systematics. And with this, we derived the improved upper limit of neutrino mass at 90% confidence level of 0.45 electron volts. Notice that this is only about 20% or even smaller than 20% of our final statistics.
Before you go on, can I just ask you about the
Sure.
first data set there?
Yes.
So what is the collaboration's explanation now why the first one is negative? Is it unaccounted systematics or fluctuation?
Actually, there's a long history of observing negative mu squared values before KATRIN. And by the time we started data taking, we already know that was from an incorrect modeling of the final state distribution. But that has been resolved. So in KATRIN, actually, we have the same modeling for all these campaigns. And the first campaign is about 1.9 sigma in the negative direction. So it's not that negative. And we think, okay, because we also don't observe following campaigns to be negative, it's probably just a statistical fluctuation. I hope that answers your question.
Don't they all have some probability of being negative? All the distributions there?
Sorry?
Don't they all have some probability of being negative? That flat, they all extend the negative range.
Yes. So I'll actually cover it later. So we have an extrapolation of model to account for the negative mu squared part. Because in a frequentist approach, we need to take into account the possibility of having fluctuations in those points that we measure background. If the background is fluctuated being higher, and we could really measure the endpoint to be above where we would expect. And that, if you take that into the model, that will represent a negative square neutrino mass. So we have an extrapolation in that sense. But by performing this belt construction, actually there's no contribution from the negative side. I hope that's clear because we always start from a true MU square being positive, and we use that to generate this belt. So I'll give you some more details about our analysis procedure. To make sure that we are not biased, we use a blind analysis, where we use an artificial final state distribution to randomly shift the neutrino mass results in its uncertainty range. So before we really look into the data, no one knows what is our best fit value. And with that blinded final state distribution, we first perform comparisons in between two different fitting teams from Monte Carlo data. And in this process, we also investigate the contribution from different systematics. And if both teams have a good agreement on all of these systematic uncertainties, on the uncertainties on neutrino mass, then we freeze these inputs in the model and we go into the neutrino mass analysis. We first have the neutrino mass being fixed and we perform roundwise fit to check if the endpoint signal and background is stable. If there's any outliers, we need to understand why that happens. If there's a reason, we exclude this from our analysis. And if we already passed all of these steps, we finally unblind the neutrino mass with real data. So we first go into the data with the artificial final state distribution. And again, if everything goes smoothly, if the both teams agreed on their results, we freeze everything, freeze the input, and we run the final analysis and publish our result. There are several challenges in this analysis because in the shifted analyzing plane configuration, different detection pixels will have different fields corresponding to the different fields in the analyzing plane. So we have to model them separately. This resulted in about 400 fit parameters in these first 5 measurement campaigns and about 1,000 data points. So computation challenge is the most critical thing in this analysis, because also for each of these steps in varying fit parameters and for each data point, we have an expensive numerical integration to calculate the expected rate. There are 2 methods to resolve this issue. The first one, what I was working on, is to try to implement a highly optimized direct model evaluation, which reduced the total fit duration to about 20 hours. And the other team uses a faster model prediction with neural network. They throw in all these input parameters and they use a training data set of about 1 million samples to get the neural network and then to predict the rate at different high voltage set points. In that sense, they have a lengthy network training, but then fitting time will be negligible. So these 2 teams are actually independent of each other. And by doing this, we are really making sure that we do correct science. And there are 2 different approaches in the analysis. The first one being the frequency analysis. We define the likelihood function to be a Gaussian likelihood for those campaigns in the normal analyzing plane configuration, where we stack data for all detector pixels together and we have a larger statistics. And for those shifted analyzing planes, because we can't stack data from different pixels, we use a Poisson likelihood due to its lower statistics. And the combined likelihood takes into account the systematics by using 2 terms. Notice that this is an illustration on how the likelihood curve evolves with negative mu squared. So as you can see, we actually have a slightly wider distribution in the negative region, but that was purely because of our model extension, and that does not show up in the belt construction. There's another approach, which is the Bayesian approach, depending on the Bayes theorem, where your posterior distribution of fit parameter data dependent on the data set Y would be proportional to a multiplication of prior information or prior distribution on the parameter and the so-called likelihood function, which is the probability of observing data Y dependent on your set of data. The advantage here is that we can apply a physical priors for those parameters that we believe that should not be negative. For example, for the square neutrino mass, we can put a prior to force them to be non-negative. And for those broadenings, we know that broadening cannot be negative, so we also put non-negative priors on them. And this makes the Bayesian analysis more robust. I would say more robust compared with the frequency one. But the drawback is that the posterior distribution would be dependent on priors. Like if we choose a prior in flat mu square or flat mu or log mu, the 90% upper limit derived would be quite different, I would say. And there's no natural choice of prior because there's no belief in how neutrino mass can be distributed before we know anything about it. But this is an interesting plot that shows how the posterior distribution evolves when you add more and more campaigns. So basically your distribution gets narrower and narrower, which means you are benefiting from having more data sets. This result will be published soon. KATRIN can search beyond neutrino mass, and it has a wide range of physical topics. One of the highlights is the search for light stereo neutrinos, with our latest update being available last week, actually. So we were able to probe the region of the claimed gallium anomaly and also the neutrino 4 discovery region. There are also searches for cosmic neutrino background overdensity. We do not have the sensitivity to really measure them, but if they cluster with a very high density, we would be able to see it. And also we have sensitivity to search for the violation of Lorentz invariance by measuring periodic signal from the rotation of the Earth. We also search for new interactions in beta-decay, but I will not talk about that details. So I'll also give you a very brief introduction on light stereo neutrino search at KATRIN. A light stereo neutrino adds on top of the standard 3 neutrino mass eigenstates as the 4th flavor. And here you can see it has a mixing and summation from 1 to 4. So basically, you add on top of the beta decay spectrum an additional stereo branch. And we detect the kink here to verify if a light stereo neutrino is seen in KATRIN. As you can see, we have a modified spectral being the weighted sum of the active and stereo branch. And we have a new result being released on arXiv this last week. This is the black curve is our 90% exclusion counter, and these purple lines are the claimed 2 sigma discovery region of neutrino 4. And also this light green line represents the allowed region for gallium anomaly. So I would say this result has fully excluded the neutrino 4 claim at more than 99.99%. And also we constrain a large fraction of the gallium anomaly region. In the last part and the last 15 to 20 minutes, I will talk about the future neutrino mass measurements. So KATRIN will finish data taking by the end of this year, but that does not mean that KATRIN collaboration will no longer exist in the future. We have a future timeline for KATRIN where after we finish the neutrino mass measurement in this phase, we will switch to a so-called TRItium phase with a major detector upgrade to search for kilo-electron-volt stereo neutrinos. And after that, we are going to perform detector R&D for the so-called KATRIN++ project, where we really want to improve our sensitivity to a comparable sensitivity with the other promising experiments and really trying to touch the inverted mass ordering region. The main ideas for KATRIN++ includes the elimination of Rydberg background, which is the main contribution to the background currently in the integration measurements. And we are also thinking of switching the integration measurement to a differential measurement with either a quantum sensor array or an electron time of flight measurement with an energy compensator. And of course, we will always benefit from an atomic tritium source to get rid of that intrinsic broadening of about 1 electron volt, which makes any effort of reducing the energy resolution below 1 eV nonsense. So I will talk about the background first. There was an idea of applying a transverse energy filter because those river background starts at a lower energy compared with beta electrons, which gives them a narrower final polar angle at the detector. So if we could perform an angular cut here, we could really get rid of those river atoms and only detect beta electrons. There are two types of so-called transverse energy filter applied in this case. So the first is called passive transverse energy filter, which filters out electrons with a large polar angle. So these parts are ruled out, and we only detect the river background to perform a direct verification of the current modeling. And the second idea is so-called active transfer energy filter, where instead of detecting electrons hitting the detector, we make the wall actually our sensitive region. And we only detect those electrons with a large polar angle hitting the side wall of the detector. In this case, we are only detecting beta electrons, but not river background. Now I will go into the differential measurement. So a differential measurement of beta energy spectrum provides us a higher statistics because for every electron, we can know its energy. And also it's nearly background free because we really have the capability of distinguish river atoms with the others because we know their energy pretty well. This is an illustration of how we could benefit from a differential measurement. And the green dashed line is the current KATRIN goal. If we switch to differential measurement, but still keep using molecular tritium source, this will be the line we will be able to reach. And if we switch to atomic tritium, then with an energy resolution of about 0.01 eV from differential measurement, we could really touch below the boundary of the inverted mass ordering. Currently, the KATRIN++ project is thinking of using metallic magnetic calorimeters as a differential measurement, with which the main spectrometer serves as a filter, which only selects out those electrons with high enough energy and reduce the amount of electrons being detected by MMCs. We also need to detector array for energy readout because these calorimeters are known to be slow and there would easily be pile-up events inside, so we have to use a large array of them to reduce the pile-up rate. On the bottom right, I'm giving you an illustration on the MMC, and a particle gets absorbed here, releases heat, which gets picked up here and causes a change in magnetization inside the loop. And that change gets further picked up by an external squeeze device. There are several known challenges. The first thing is that these devices has to be under cryogenic operations at a temperature lower than probably 100 or 200 millikelvin. So it's challenging to couple this cryo platform with a room temperature main spectrometer because we can never cool down the 14-meter main spectrometer down to 10 millikelvin. And also it's challenging to reduce the magnetic field from wherever we have the detector, about 2.5 Tesla, to 20 millitesla, which is the maximum magnetic field that NMCs can work with. And as I have also explained, we need to use a large array of detectors. So we are facing an issue of multiplexing of about 10 to the 6 channels. To answer these questions, the KATRIN team is now working for the electron and concept projects to verify if it is possible to use MMCs for future neutrino mass experiments. The electron project has already finished, and it verifies that MMC detection can actually work for external electrons. And we verified it with electron source being either egon or beryllium, krypton, and also tritiated graphene, which is of specific interest for polymers. And we succeeded to measure for the first time the differential tritium spectrum with a cryogenic microcalorimeter. Following the success of electron project, we are now doing a so-called concept plus project, which investigates if MMC arrays can be integrated into the KATRIN beamline, and also investigate the potential systematic effects attached to this technology. Besides the previous differential measurement using quantum sensor arrays, we have a new idea of measuring the time of flight for electrons to perform a differential measurement. As this has been demonstrated in the energy loss calibrations, we have an energy-dependent time of flight, as you can see on this plot, for those non-relativistic electrons. The challenge is that we have a good timestamp at the detector, but we do not have a good timestamp when the electron starts traveling into the spectrometer. So the current idea is that in between this selection, this pre-spectrometer selecting all the electrons and the main spectral analyzing it, we put in two devices. One is TEC, I will explain later, and another one called an e-tagger, which gives us a precise timestamp without changing much of the electron energy. There are two options that we have in mind, but these are very, very preliminary. The first idea is that we use image current for those electrons passing by a superconducting loop coil, and this image current can be further read out by slit. And we were also thinking about using a 2D membrane in this plane with superconducting nanowires to read out the single phonon excitations from electrons passing through that membrane. And besides the electron tagger, we also need to reduce the transverse energy, or to make our main spectrometer better in energy resolution. This is the idea of the introduction of so-called transverse energy compensator. And as you can see, currently the main spectrometer works by converting all its momentum into longitudinal direction, where there are still remaining parts in the transverse direction. And the longitudinal part does not have an equal energy because of the total energy is conserved. The idea is, if we really apply a boost, which is angular dependent, which can make the longitudinal energy being almost the same, then we can get a narrower bandwidth of this time of flight measurement. And in this case, the total energy actually is not exactly the same. So here there are some simulations with this compensating energy, and without it, as you can see, we have a huge improvement with the compensator in its energy resolution, or its actually time resolution. With this technology introduced, we can have an energy resolution being improved to about 0.2 electron volt. This has been demonstrated in Münster, but the result is still not published yet. And the last but very important part is the atomic tritium source, because it has no intrinsic broadening when compared with molecular tritium. And it is a necessary technology for a sub-eV energy resolution. To provide atomic tritium, we need to craft molecular tritium at a high energy, because there they have a higher kinetic energy, and they can easily flow away from the molecular bounded state. But then to confine those atoms and to suppress Doppler broadening, we need to further cool down those hot atomic tritium to a temperature range of millikelvin to 1 Kelvin, and that's the most challenging part for now. To avoid recombination of these atoms, a technology called evaporation is adopted, where we continuously reduce the magnetic track, and those atoms with high kinetic energy will evaporate, only leaving those with extremely low energies inside the trap. So as we gradually decrease the magnetic field, the temperature got also decreased to about millikelvin or Kelvin level. There's a joint effort in the KARlsruhe group and also the Mainz group on this project. And it is in preparation for the future use of both KATRIN and say Project 8 or the other experiments. Now talking enough about KATRIN, let's take a look at the other experiments. There are some experiments using another isotope holmium to measure the electron capture spectrum from their decay. This electron capture process has a Q value about 2 keV. So they have even more effective statistics compared with a tritium beta decay. The main effort comes from the ECHO and Holmes experiment, one using MMCs and another one using TES. To reach a sub-EV sensitivity, they need about an activity of 1 megabecquerel of holmium. But the challenge there is that they can't really confine atomic tritium inside either an MMC or a TES microcalorimeter. The Holmes experiment have just published their results from demonstration runs and derived an upper limit of 27 electron volt. So they have successfully verified that the technique works and they only need more funding to go to larger scales. The main challenge here is that we don't have a good prediction from theory of modeling these peaks, these the peaks of the energy levels from the excited states, excited final states, and also that they have to use a large arrays of microcalorimeter to reduce pileup. There's Project 8, which looks into differential measurement with radiation frequency. Project 8 collaboration also uses tritium as beta decay source, and they perform differential measurement not in its energy, but in the frequency domain. This is an illustration of how the signal looks like. The electron detection is performed by measuring cyclotron radiation emission because electrons will go like in circular in a magnetic field and emit gammas corresponding to their energy. This is the main focus on phase 1 and phase 2. After that, the Project 8 collaboration is also trying to investigate the usage of mode filtered resonant cavity. That basically arises from the challenge of a small radiation power if they go to larger devices. And also, this Project 8 experiment also depends on atomic tritium source to really go to their final sensitivity, reaching inverted mass ordering. I believe there are many local experts on Project 8, so I will not talk about all the details. Also looking at CREST, there's another group in the UK forming a quantum technologies for neutrino mass, namely QT&M collaboration. And they have in mind a demonstration apparatus which stores those atomic tritiums inside the ring by magnetic fields and then use quantum limited amplifiers to measure the CREST signals in this ring. They are currently investigating a precise magnetic field mapping, but I think that's also very interesting for the Project 8 collaboration. Another collaboration that is claiming that they have sensitivity on neutrino mass search is Ptolemy, which has a combination of all possible techniques, the RF tracking, the transfer sweep filter with EM fields, and also the TES microcalorimeter. The source there is a compact tritium absorption on graphene. And they claim that they have an energy resolution reaching 0.1 electron volt. This experiment was proposed to measure cosmic neutrino background with a kink being 2 times neutrino mass separated from the endpoint energy. But from this, they also have sensitivity to neutrino mass, of course. Their main challenge for now is that uncertainty in principle on a single layer of graphene limits their energy resolution, and new structure to delocalize tritium atom is under investigation for them to reach the desired precision. To summarize, the KATRIN experiment is still current state of the art, And it has published an upper limit of neutron mass being smaller than 0.45 electron volt at a 90% confidence level with only 20% of collected statistics. KATRIN is finishing its data taking for neutrino mass space by 2025, and it is expected to reach a final sensitivity of about 0.3 electron volts. The R&D is currently ongoing for the next generation upgrade of KATRIN, namely the KATRIN++ project, to push down neutrino mass sensitivity to the inverted mass ordering region. There are several differential detection techniques that we have in mind in all of these neutrino mass measurement collaborations. The first one is the electron time of flight measurement, still with the current KATRIN main spectrometer. And the second is cryogenic calorimeters, for example, the transition edge sensors used by the Holmes and Ptolemy collaboration, and also metallic magnetic calorimeters currently being used by ECHO and also proposed to be used for KATRIN++. In addition, there is press spectroscopy measuring cyclotron radiation from electrons. That's mainly probed by the Project A collaboration and recently also by the QTMM collaboration in the UK. On top of all of this, to reach an inverted mass ordering or to reach an energy resolution of less than 1 electron volt, atomic tritium source is indispensable. And with that, current R&D is ongoing in Karlsruhe and Mainz, and hopefully we will have the first demonstrator being available in the next 2 years. With this, thank you for your attention, and I'm open for questions.
For the talk, time for some questions.
Great talk. Could you say more about the cosmic neutrino background and how KATRIN is sensitive to it? Like is it interactions with the tritium in the column and then like the observable?
Yes, sure. So yes, we have sensitivity to cosmic neutrino background. I didn't go into the details in the introduction for Ptolemy, but basically there, instead of observing a tritium beta decay, we absorb a neutrino from the universe. And over there, the neutrino mass is added on top of the available kinetic energy. So it provides a kink of 1 mu above the endpoint, which was predicted with 0 neutrino mass. And as you can see, So as you can see, it has the standard spectrum from tritium beta decay, and it has another kink being 2 mu above it. So that's a combined spectrum. And if we really detect a peak above the endpoint, we know that we measure cosmic neutrino background. But the reality is KATRIN has a background which suppresses all these contributions from statistical fluctuations. And if cosmic neutrinos are at its predicted density, then we will no longer be able to see it. So we probe the so-called overdensity, which is a multiplication factor for the prediction, because cosmic neutrinos can also cluster around the Earth due to gravitation effects. And the best limit for now is from the first 2 data sets, and we constrained this overdensity fraction to be smaller than 10 to the 11. So you can see how a huge gap in between KATRIN and the real measurement of cosmic neutrino background is. I hope this answers your question.
Nobody's ever detected a cosmic neutrino.
Well, Ptolemy is trying to do that. I mean, in principle, they can do this, but they also have a few challenges, like I have mentioned. If they do not delocalize those tritiated graphene, they would be limited to an energy resolution, with which they cannot see any cosmic neutrino background. So that is a very long-term thing. I would say cosmic neutrino background will not be detected in the next 20 years.
I guess a related question. I mean, doesn't Holmes and ECHO have the same problem that they're in a solid source and they have this like 0-point broadening, at least in principle, or is there some reason that doesn't apply to Holmium-163?
You mean for cosmic neutrino background?
Well, not just for the neutrino mass endpoint. Like, I mean, have they looked at what the equivalent localization effect does on their spectrum in terms of smearing out the resolution?
I think the thing is that Ptolemy has a single layer of graphene, which means you are really localized. But in the case of Echo and Holmes, they are implanting holmium into the MMC and PES. It is not necessarily localized because it has a thin layer, but not as thin as a graphene layer.
Okay, that's a really interesting question. I'd love to talk more about that.
Yeah.
So, for the atomic tritium upgrade for KATRIN.
Yeah.
Would the idea be that the atomic tritium source sits in the place of where the molecular source is now? And would you would still have to transport the electrons from the atomic source over through the spectrometers, right?
Yeah, that's true. And actually, the concept is still not clear yet because we are at the very early stage of trying to think of how to move forward. And the idea now is that we replace the molecular tritium source by the atomic tritium source. But the actual implementation, how we arrange for this tritium loop is still unclear now.
Yeah, thanks for a nice talk. So when you talk about setting the neutrino mass limit, you talk about two methods. One of them is frequencies, and then the other is using a neural network. No, but I think you talk about a neural network as well.
Yes.
So what is the difference between the two of them? I guess for frequencies, you're trying to minimize the negative log likelihood.
Yeah.
The neural network, there's like some cost function that you're trying to minimize. So what's the main difference? And then a follow-up question is, which one do you decide to use, or is there any averaging that you do for that?
Yes, that's a very nice question. So actually here, neural network only predicts the detection rate at different high voltage set points. So there's no difference. It's just a replacement of the standard modeling to reduce the computation cost. But I would say both of them works as in the same framework using frequencies approach. The only thing is that with a neural network, they would improve their computation speed by a factor of 10,000 or so. And also with direct optimization or model evaluation, we can also do that. So it's basically like two teams are based on different implementations of the same model, but then they also have different treatment to optimize the computation, which makes these two teams independent. Yeah, so neural network here is not really using a fancy form. It's only used to predict the event rates at different retarding temperatures.
Questions?
I have another question about the time of flight approach for KATRIN. So how, I guess naively, I would assume that pilot would be an issue. Like if you need to tag the electron start to finish.
Yes.
So what are the, I guess, ideas of how to approach that?
That's a very, very good question. So that's why we still need the main spectrometer. Let's say electrons start at about 18 kilo electron volt. If we still apply a high voltage at the main spectrometer, say 30 electron volt beforehand or lower than that, we only select out electrons in the last 30 electron volt of the spectrum. And by doing this, we are reducing the amount of events that we finally detect. So yes, and also for differential measurement, I don't think we need the last 30 electron volt. We only need the last 10 electron volt or even 5 electron volt, and that really helps in reducing statistics.
Can you just go back to the systematic slide that you had for the final sensitivity of 0.3 eV? What is the improved? So that would be the improved systematic that you're assuming then for the full data set?
Yes, so here I'm quoting the Chem 5 campaign. And actually for all the following campaigns, we basically have the same setup as the 5th measurement campaign. And as you can see here, we got rid of a background over dispersion, which I actually didn't introduce because that's too detailed. We did not observe any of this by using an asymmetric field configuration. And by turning off pre-spectrometer, we also don't have any time-dependent background from that panning tab. Also by spending more measurement time and using a higher activity calibration source, we can also constrain pretty well those other dominating SNAP alternatives. And for now, the only thing left is the gas density and energy loss, because we don't have a precise modeling to explain the discrepancy we see in the different modes of calibration. But that is expected to be resolved like in the next year. We already have some explanation, but that's not public yet.
Great, thanks. Any other questions? Otherwise, let's wrap up. Thanks again for the nice talk.